and this begins EE 555 discussion, Wednesday, April 16, 2014.
Okay, good morning, everybody. So today we'll talk, we'll see some problems on optical networks and specifically on logical topologies and things like this. Sorry for the bad voice. I have a cold and I'll do my best. Okay, so let's start with the first problem. Consider an optical network with 8 nodes. Each node can transmit and receive on 2 wavelengths. Each wavelength can support S bits per second. Traffic is uniform. You are to consider various designs and find the maximum throughput. Okay, that's the final objective. All nodes share a single medium, passive star, but different logical topologies are used. The nodes are connected, in the first case, the nodes are connected in a bidirectional ring fashion. In other words, node X is connected to the node X minus 1 and node X plus 1, mode 8 all the time, right? And in the other case, we have an 8-node perfect shuffle. Do you remember that from yesterday's lecture, or you didn't cover that much? Passive star. The perfect shuffle we'll see the topology, how it looks over here. Okay, so for each of these networks, we need first of all to sketch the network connections between nodes, sketch the path from node 0 to all other nodes, not including that, not assuming that somebody sends to himself, and then compute the average number of hops, the total aggregate capacity, the capacity per user, and which network provides the maximum capacity per user. And we'll continue with the rest of the questions as you know. So let's start by first analyzing the topology in this particular case, in the case where we have a bidirectional ring. All right, so the first question is sketch the network connections between the nodes. And the main objective, as we said, is to calculate the maximum throughput, right? So do you remember the equation for the maximum throughput? Most likely you haven't seen it yet, I think. But it's in the next lecture, if you haven't seen that yet. And we won't prove it here. We'll just use it. So the aggregate capacity of a multi-hop network is N times R times Q divided by expected X, where N is the number of stations, Q is the number of wavelengths per station, R is the data rate, and expected X is the average path length. Okay? So, in number of hops, of course. Hops taken by the inhibitor cell, reaching the destination, we represent that as, X. It's a random variable. So, let's capacity total, as we said, equals CT equals, in this particular case, we don't have, we can use just the same notation, N times R, or over here we call it S. So I'm going to use S times Q divided by expected X. Okay? Capacity per user equals CT total divided by N. We just eliminate N. Okay, so now over here in total stations, this is not 5, this is S. S is, rate. Data rate, BPS. And Q is the number of wavelengths per station. Per station. In our case, this is equal to 2, right? In our case, this is equal to just unknown, S. We don't have anything. And in this particular case, how much is the number of stations? How many? 8. Okay? Alright, so with that said, we have the questions for the maximum throughput, and then we want to see which topology achieves maximum throughput. For the guys that just arrived, very quickly, we have an optical network of 8 nodes. We have each node transmits with 2 wavelengths, and we have uniform traffic, and we want to see which topology achieves maximum throughput. One is the nodes are connected bidirectional ring fashion, and the other is an 8-node perfect shuffle. We'll see what it is. Okay, now let's draw the first topology. Bidirectional ring. So I guess you know how it's gonna look, right? I'm gonna do my best here. All right. Now, we have bidirectional connectivity, so we have all the arrows here. And the other way around. Okay? Now, sketch the network connections between nodes. That's A. And we will do the next one for the 8 perfect shuffle shortly. Sketch the path from node 0 to all other nodes. We want to sketch a path node 0 to all other nodes, okay? Which one is better to do? Let's see A and B for bidirectional ring. And then we'll do the other case. We have 2 cases, right? So the paths from node 0 are 0, we have all the possible. If we want to go to 1, we just stop to 1, But if we want to go all the way to the possible what's going to happen? If we want to go to 4, we'll go to 4. If you want to go to 5, Alright. So here we have 4. We have here 5. Make sense? Okay. Now that's the path from for this particular case. Now let's do the same in the next page for the perfect shuffle. The perfect shuffle will look like this mesh over here. Interesting. Have you seen that? Okay, it's coming in the next lecture, I think. And this is just a few slides after you stopped yesterday. We don't need, the professor will go over it and analyze, why things are happening like this. But in any case, just keep in mind how the basic connectivity is, like from switch 1, lambda 1 goes to the next one, and then we have lambda 2 here, and then lambda 3 to the other 2, and then this, it goes to the first ones, and then the fourth, it goes to the last 2. Okay, we'll replicate the same thing. So perfect shuffle, we have over here, we have 8 switches. So 0, 1, 2, 3. And then we have, 4, 5, 6, 7. And then we have a circulating, right? We have circulation in this case. We will see how we can achieve that. This is achieved through a bus. Okay? And we will basically connect those back to 0. Now, following exactly the same pattern, the connectivity will look like this. And this will go down here. Okay? Now, for number 1, it is connected to 6 and 7. Number 2, 1 and 4 and 5. And number 3, 6 and 7. Alright? Now, those 2 guys, 4 is connected to 0 and 1. 5 is connected to 2 and 3. 6, same thing. Okay? And 7 is connected to 2 and 3. Perfect shuffle. Now, the paths, perfect shuffle, paths from 0. Okay? Let's draw the paths from 0 to all the possible destinations. So in this particular case, it will be, we need to draw the same thing. Four, 5, 7, 6, 7, 0, 1. Okay, from 0 to 1. We have this path, 0, 4, 4, 1. Okay? 0, 2, 5. Then 0, 3, 5, 3, right? This one. Then 4, we have a direct link. 5, we have a direct link. 6, we go to 1 and then from 1 to 6. Okay? And that counts as 3 hops actually. We go in 7 similarly. Okay? So we have all the paths and now we should just do the calculations to see which one is more efficient, achieves higher throughput. Okay. Now what questions have we covered? We have covered the first one, sketch the network connection, sketch the path from node 0, and then now we go to C, compute the average number of hops. C, for bidirectional ring, expected number of hops, excuse me. Let's go back to the ring. How do you find the expected number of hops in this particular case? What do we mean by that? We mean, let's assume we start from a given node, okay? Assume we start from node 0. We want to randomize it and say, okay, what's the expectation if we start from 0? If we start from, we just fix that, and then if you want to go probabilistically completely, what you should say is, I want to calculate the expectation for a random destination. I want to calculate the expectation of the number of hops, the expected number of hops. Okay? So the random destination is what? How many random destinations you have if you start from node 0? 7. Exactly. So if you want to go completely probabilistically, you use conditional expectation. Okay? Or the law of total expectation as it's called. If you want, I hope you remember this thing, so let me write it down. Summation of expected hops given destination J, P destination J equals 1/7 times, there you go, 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. Very good. Okay? So that gives you 16/7. Do you agree? I'm giving you this formula just to give you some more intuition of how you can do it theoretically, just to be confident of what we're doing. But essentially, we assume that we start from a given node, we assume some random destination, and then we calculate the expected number of hops for this destination. This means that in this particular case, total capacity is equal to 2 times 8 times S over 16/7, and this gives 7S. And also this gives CU for the user, capacity per user, 7S/8, because we have 8 nodes. Make sense? Alright. Now, for the other guy, the expected number of hops for the perfect shuffling expected number of hops, same logic, is equal to what? Eh? Why? Oh, okay. You did the calculation already? That's awesome. Yeah, it's 2. Let's see why. Where is my figure? Oh, it's over here. All right, so we have for 1, we have 1 over 7 first of all, same logic. 1, for 1 it's 2, right? So I'm starting with 2, plus for 2 is 2, for 3 is 2, for 4 it's 1, for 5 it's 1, for 6 it's, we should go to 1, 1, 2, 3. And for 7 is 3 as well. And this gives you 6 plus 2, 8 plus 6, 14. Over 7 equals 2. You agree? Okay. That's perfect. So we found, oh sorry, you didn't see the screen. In this particular case, the total throughput will be 2 times 8 times S over 2, and this gives you 8S, and this, the capacity per user is S. Which one achieves higher capacity? Perfect, Saflin. Provides max capacity per user. Okay? That's fine. Now, what else is left? Okay, now we go to part D that we didn't read earlier. Draw the physical bus. Sorry, it's too early, guys. I can't speak. Draw the physical bus topology with wavelength lambda assignments for the 8-node bidirectional ring logical topology above. How many wavelengths are needed? Suggest another physical topology that may reduce this number by 50%. Anyway. Let's see. So we go back to, this is part D, and we go back to this topology. So the question asks, draw the physical bus topology with wavelength assignments. How would you assign wavelengths to achieve this connectivity? Physical bus topology. For this particular 8-node bidirectional ring, this is the logical topology, right? You know the difference? Over here, the connections, they mean light paths, right? It means where the light is going. And we can have either one hop straight, like one same wavelength in a link, or we can have multiple. If we cannot achieve, like, because of multiplexing and problems like this, then we might have some node changing the wavelength, okay? And we can achieve multi-hop light paths. So we want to draw now the physical bus topology, the underlying topology, the connectivity. Okay, let's start doing that. It's kind of a weird figure. Over here, you haven't seen that yet. Most likely we'll see more details in the class. But we'll do the topology here and you will do the wavelength assignment at home. Okay? So it's pretty easy. I'll show you. And you have also an example in the lecture. Now, the way to achieve that is, as we said, is using a bus. Right? If you remember, we'll try to draw this graph over here. I'm showing you a picture first in order not to freak out from my drawing, and that's what we want to achieve. This bus connects the output to the input. Okay? And let's see how we can do that. I'm going to draw the same thing. You can use whatever numbering you want. 0, starting from 0, starting from 1. S3, S4, S5, S6, S7. And here can this figure support the topology we want? This physical bus, this physical topology? Each node has 4 arrows, let's say, okay? 2 inputs, 2 outputs. So we agree with that. It also needs to have 2 wavelengths, okay? So you will use that information to assign the wavelengths and achieve this connectivity. Okay? Complete the wavelength assignment. We'll just start by just giving you an example. So we want this guy to be connected to this guy, right? So if this guy uses this wavelength assignment, what is the wavelength assignment over here? I mean, the fact that if it's 1 or 2, you can choose, but you can just, you know, make your own choice and follow it all the way, okay? So you should continue this assignment all the way for all the nodes to support this connectivity. Now, we do something similar here, okay? Now the problem is how many wavelengths, different wavelengths we need for supporting this thing. How many? 16, exactly. Right? So the total, do you agree? The total wavelengths needed is 16. We cannot reuse really the wavelengths over here. So the next question that is related to that is how we can reduce this total number of wavelengths to half. You haven't seen this graph. I don't expect you to come up with that, but it's basically you can think of it like splitting, your graph is connected like this, okay? You can split inputs and outputs maybe to two different classes and separate them and make the graph, make half the graph, no, make a node communicate with half the graph only and not the other way around. Okay, that's what you should do to achieve reuse. So if you do that, the graph will look like this over here. That's what I'm going to try to do. Okay? So, all right. Pretty involved. We have two buses. Now, let's think about it. So we start you should remember how to draw this topology, really. Have the outputs go to the first bus. Yes. Eh? The rest goes to the upper, right? Exactly. So okay. Now what about the inputs? Oh, nice. Where should I fit this now? Thanks, guys. Okay. Now the input we will have you can do in this case, particular case, you can do it symmetric, but you can do your own assignments, right? Meaning you should put the labels and see how each one should look. You see what I mean?
The time is 23
okay,
o'clock.
we should find, we want to support this connectivity over here, right? So in order to support that, we need to put labels here and say, okay, this is S1, S0, and so on and so forth. You know what I mean? So that's what I mean by that. And also you need to allocate the wavelengths over here. Make sense? Okay. So one way to support this is think about this. 1, 2, 3, 4. We have 2 points where the 2 halves are connected. 0 and the 4th, no, the number 3, right? So in this particular case, to support this connectivity, we need one port to connect to the first bus and the other to the second bus. So the rest can be sequential, right? The same way. Oops, this is number 4. Needs to. Now let's think why this works. I hope I didn't mess any arrow over here. What do we want to achieve, guys? We want to connect 0 to 7. Do we do that? 0 is connected to 7, right? How about 0 to, what's 0 to 1? It's connected through this bus. Make sense? Okay. How about number 4? I mean 0, 1, 2, 3. Same, right? Okay. Great. So now can you continue this and put the wavelengths again? So okay? Right. Now, it's a long problem. And we're running out of time. Okay, for the bidirectional topology, suppose node 7 fails. Okay, sketch the path from node 0 to all other nodes and find the average number of hops, the traffic that is generated at node 0 and destined to nodes 1 through 6 will encounter. Assume uniform traffic. How would you rearrange the wavelength assignments to minimize the average number of hops for node 0? Okay. So in this case, the question asks, find the if node 7 fails, what happens? Everything needs to go the other way around, right? So in this particular case, if 7 fails, the path should be 0, 1, 2, 3, 4, 5, 6, and we stop wherever we want. In this case, what is the expected number of hops? We have 6 destinations and 1 plus 2, right? Plus 3 plus 4 plus 5 plus 6. Do you agree? 21 over 6, because we have only one way to go. One way to solve this problem and make a new wavelength assignment that is more efficient, the question asks, how would you rearrange the wavelength assignments to minimize the average number of hops for node 0? What we want to achieve, this is a logical topology, as we said, right? The previous was a logical topology. So we should assign the weights in the wavelengths in a new way, such that we virtually connect 0 and 6. 0 and 6, correct. In order to avoid going the other way around, right? That's what we want to achieve and get rid of that unnecessary hops. So the new wavelength assignment should support the following paths. 0, 1, 2, 3, and 0, if you want to go to 6, 5, 4. Okay? And in this particular case, expected number of hops is equal to what? 1, 6. Now it's 1 plus 2 plus 3 plus 3 plus 2 plus 1 or whatever, and this gives 2. Perfect. Okay, so that's all we need to do. Now let's go to the next problem. It's much shorter. Do you have questions on that, guys? Okay. The logical topology shown in this figure over here, this is a logical topology, it's a hypercube, and is implemented on an 8-node passive star optical network. Each link represents the ability to transmit in either direction. Okay, this means that this is a double link. We can transmit either way. There is a logical link from 000 to 001 and the other way around. For a uniform traffic matrix, every node sends to every other node at the same rate. What is the average path length in a virtual topology? Then how many wavelengths are needed? And if we have OC 48 lines, what is the maximum end-to-end traffic that the network can handle? Okay. Looking at that nice figure here, what do we see? Okay. What is the average path length in this case? That's the first question. How would we proceed? So first of all, the first thing we need to understand is that we have a logical topology, which is this one, and this is implemented using a physical topology, which is an 8-node passive star. Okay, so to support this, what should be the, let's draw the star first of all, and then we'll see how the connection should be in order to support this virtual topology. Okay, so 1 1 0 0 1 1 1 1 1 0 0 1 1 0 1 0 0 0 1 0 0 0 1 0, and so on and so forth. Now this is connected like this. Okay, that's the ring, the physical ring. However, in order to support this hypercube, as you see over here, for example, 110 is connected to 010. We have a link. I'm going to draw it like this. We have another link to 100. Okay, we have another link to 111. Okay, we should do the same for all the nodes and build the underlying network. Okay, so I'm continuing this. This will look like this. This should go. It's basically 2 squares if you think about that. So this should be connected to. You can verify at home. Okay, we have 1 square, another square. Do you agree?
5-minute warning.
Thank you. And also we need this connectivity 100. This is connected and this. And 111 to. This graph should be enough to support this logical topology. Now, what is the expected number of hops in this case? Assuming we start from 0, 0, 0, from, I don't know, some node. How many destinations do we have? Okay, 7. So we have 1 over 7 times, we have 1, 2, size 1, okay? And 3 of size 1. So it's 1 times 3 plus how many? Size 2, 1, 2, 1, 1, 2, 1, 2, 3. And size 3? This node here, right? One times 3 equals 12 over 7. Do you agree? Okay. Now, what is the wavelength, the number of wavelengths we need to support this connectivity? So, how many wavelengths are needed to implement this network? Number of wavelengths. How many edges do we have? How many edges? It's not 8, it's 12, right? Not nodes. How many connections? 12. So if you want to support bidirectional connectivity as it's given though, how many wavelengths do we need? 24, right? Double. Because of the bidirectional connectivity. Number of edges times 2 bidirectional connectivity is equals 24. Okay. Now, in the last question, we have 3 minutes left. But it's shorter. So each link can carry an OC48 channel. Okay. What is the maximum end-to-end traffic that the network can handle for a uniform traffic pattern? Each link in this network can carry 2.5 gigabps. So the question is, what is the maximum end-to-end traffic? Maximum end-to-end traffic. How much traffic basically there is in the network, okay? End-to-end. So for that, usually what we should calculate is the total traffic inside the network, okay? And then we know the average hop count, so we can calculate on average how much traffic is inside the network end-to-end. So let's do that. The total traffic or the total flow inside the network is 24 times 2.5 gigabps, and this gives you 60 gigabps. Why is that? Because we have 24 links of this size. Now, you remember from the flow problems when we had the external rate, external traffic arriving, right? So basically, the external traffic was used to see how much basically we can afford in the network, right? That's the total network that the total traffic that the network can handle. So we can use the same approach here and say that total flow equals external traffic rate times average path length. External traffic into the network.
Out of time. I'm sorry.
Yes. And this gives you, if you solve in terms of gamma, gives you that the end-to-end traffic that the network can handle at most is, we solve in terms of gamma, 6 gigabits per second over 12 over 7, and this is 35 gigabps. Okay? Let's discuss that if you have questions after we close. Okay, thank you very much.
And this concludes EE555 discussion on Wednesday, April 16th, 2014.
The time is 0 o'clock.